Let's start just now. We have a pleasure today to have a talk by Dr. Nava Gaddam from Utrecht University. He will tell us about applications of black hole scattering. Now, please, 1 hour.
Thank you very much. I'm very grateful for this opportunity to speak to all of you and advertise some of my work. Luca already asked me. I'm very happy to stop for questions, although I'm going to be talking a lot. Please feel like the boss and complain if you don't like what I'm saying, or if you have questions halfway through, stop me whenever and leave the burden on me to finish on time. And I'll find my way. So I'm going to talk about some applications of scattering in the presence of black holes. And this talk is mostly based on the first 3 papers that I listed here that appeared. 2 of them appeared in December 2020, and 1 that appeared a few months ago in October 21. And towards the end, I guess some of you may have heard some version of this talk in the recent past. Towards the end, I'll say some things about some upcoming work in a few that's to appear in a few weeks. So most of this work is done in collaboration with Nico Groenenboom, who's a very bright graduate student with us in Utrecht, and Gerard het Hoofd, who doesn't need any introduction. And some of the work that I'll mention regarding soft theorems that emerge near the black hole horizon is something that I'm working on together with a graduate student in Brussels, Ankit Agarwal. So before talking about scattering, one has to understand the free theory in the first place. And this is something that all of you are very familiar with. And this is an image that you've probably seen since your kindergarten days. So I'm going to quickly run through Hawking's argument for why there is information loss. And the statement is as follows. Consider some infalling matter. These are the curved lines that are going from bottom to up that start at scry minus, so past null infinity, that collapse, that radially fall in and collapse to form a black hole. And now consider modes that the black hole is going to radiate that reach scry plus at future null infinity. So Hawking argued that the vacua at scry plus and scry minus are different. And so he wanted to compute the number operator. So he tried to extend the modes that you receive at scry minus, so at future infinity, all the way back to the past. And he observed that these are related by some Bogoliubov coefficients in comparison to the modes at scry minus, and these were thermally correlated. So the statement was that no matter what you throw into the black hole, you end up with thermal radiation at scry plus. Therefore, there is information loss. And this is a theory that is free, meaning that you're at quadratic order in perturbations. We're working with free scalar field that's propagating on a fixed black hole background. The main essence of what I'm going to talk about has to do with tracing these modes back from scry plus near the horizon. So as you take these modes that are received as scry plus and you go backwards in time, this is called geometric optics or ray tracing that Hawking used. As you go close to the horizon, these are not really far apart. They're not asymptotic states. And I want to argue that they receive small corrections, that you cannot treat them to be free when you're near the horizon, that they are interacting and the interactions are mediated by fluctuations of the metric. So the background cannot be treated as being fixed, and there are interactions that are mediated by these gravitons. So that's the essence of what I'm going to talk about, that these interactions are important and they result in quantum mechanical scattering amplitudes that will change Hawking's picture. And I want to discuss various applications of considering such scattering processes in the presence of black holes. That's sort of an elevator pitch, if you like. So we're interested in studying what happens when you have particles that are falling into a black hole. And the statement is that if there are particles that are very far apart and are not very energetic, of course, they don't interact. They just miss each other by a huge impact parameter. They don't talk to each other. They just go uninterrupted. But even if they're very far apart, if you start increasing the center of mass energy of these collisions, then what happens is that they exchange soft gravitons. And this is what is called the flat space iconal regime, where you have metric perturbations that mediate interactions, but there is nothing dramatic that happens because the impact parameter is very large, the particles are interacting at very large transverse distances. But as you reduce this transverse distance, so when you have small enough impact parameters, I put small enough in quotes because it's important to compare with the appropriate scales. And I will be very precise about what I mean by small and large. But roughly speaking, when the impact parameters starts to compete with the energy scale associated, or the inverse energy scale associated with the scattering, then you expect black holes to form. So the statement is that as impact parameters are smaller, you cannot ignore gravitational interactions. And the basic question is, can we calculate these amplitudes? So one might ask, when there are such nonlinear effects of gravity, why do we expect that we can even calculate anything? Why should such a regime exist where you can actually calculate something in effective theory? One sort of a defeatist argument is, you can say there are many indications that the information problem is resolved in effective field theory. It almost doesn't matter which picture you look, which proposed resolution you look at, may take the islands or the principle of holography of information. The overwhelming perception is that the information problem can be resolved in effective field theory. There's another important aspect to gravity, which is that quantum effects, unlike in quantum field theory, which arise only due to large momentum transfer, you also have emergent scales, which give you quantum effects. The information problem is itself an example that this is a problem that emerges at large scales with large black holes. And so we believe it to be a quantum mechanical effect. So there is something to be said about why in effective field theory, you should be able to calculate such amplitudes. What I said is not good enough to say that just calculating these amplitudes is going to resolve the information paradox, but it's an indication that these things can be calculated in effective field theory. And when it's possible, when we know that they're going to give us corrections to what Hawking computed, why not do it? So in this talk, what I'm going to do is to carefully define this regime in effective field theory, where you can calculate these amplitudes. I'll discuss the calculation of some amplitudes and what they imply. And there are many interesting applications that emerge from the existence of such a regime in effective field theory. And one of the things that I would like to single out is that there's a new emergent soft limit near the horizon, which I think leads to emergent soft theorems near the black hole horizon. There are some other applications too. So depending on how we go with time, I'll end with some applications and conclude with that. So here's my plan for the talk. It's fairly simple. First, I will just review what is known in detail about large impact parameters, which is the iconal expansion in flat space. Then I will discuss what happens when you reduce impact parameters, where you expect classical black holes to form. And then in this smaller impact parameter regime in phase space, I will calculate or sketch the calculation of some scattering amplitudes and their implications. In particular, interesting scales associated to the physics that we expect emerge. So for instance, from the 2 to 2 amplitude, you get the scrambling timeout. And from considering particle production, you get page timeout, which is very interesting. And then I will explain to you why and what the emergent soft limit is near the horizon. So before I begin with discussing large impact parameters, is there any quick question that arises from based on what I said?
Okay. Excuse me, maybe I will ask, how will be your consideration, especially in 4-dimensional case, or the dimensionality is not so important for you?
I think all the formulas that I will write down will be 4-dimensional. I think it's important, because I'm talking about metric perturbations and gravitons mediating interactions, that it's important that gravity is dynamical. So I think it has to be greater than 3 dimensions. And I will expand all my formulas in a partial wave basis, so in spherical harmonics. And because I'm in 4 dimensions, I will discuss this with the 2-sphere spherical harmonics, YLMs. But if you're in a higher dimensional space, then the horizon is just a higher dimensional sphere, and everything that I say to leading order carries over once we expand the spherical harmonics for the higher dimensional sphere.
Okay, thank you.
Thank you for the question. Anything else? If not, let me move on to discuss large impact parameter scattering. So let's take just flat space, the Minkowski diagram, where you have a particle that is colored in red, that's traveling along some null coordinate. And now let's take a test particle that's in green, that's going to scatter against this red particle. Because it's a conformal diagram, of course, it looks like they're head-on colliding, but of course, there's a transverse distance in question. And here I'm thinking of two particles that are separated by a large transverse distance. So these are particles that are colliding like that, but then there's a large transverse distance between them. For this interaction to be important, how do I phrase it? So let's look at the impact parameter. And what do I mean by the impact parameter being large? Firstly, we want it to be much larger than Planck scale, because we don't understand Planckian physics. The other interesting scale in the theory is the scale associated to the scattering energy. So because the coupling constant is dimension full, you can form a length scale, which is G Newton times square root of S, where S is the Mandelstam variable associated to the total center of mass energy. And we want the impact parameter to also be larger than any scale in the theory. So in particular, larger than Planck scale and G Newton times square root of S. So even though the impact parameter is very large, the energy associated to this collision is given by 1 over G Newton times the test mass of the particle. So if it's a very light particle, this energy can be very high, which means that you cannot ignore gravitational back reaction. And this is very well known. And what happens is that the green particle just gets kicked along its longitudinal direction because of the red particle. And this kick can explicitly be calculated. And this, in fact, is also a solution to nonlinear Einstein's equations, where the null coordinate gets shifted a little bit. And this back-reacted metric is called the Eichelberg-Sechsel shock wave. And this is studied in a lot of gory detail. This is sort of a classical picture of how to think of this scattering problem as a back reaction on the geometry. One can also understand the same story of scattering in terms of Feynman diagrams. And how do you do that? Here's how it goes. First, we're looking at flat space. So we work in the background field method, where we expand our metric as eta mu nu, the flat metric plus metric perturbations. And we look at interactions that are generated by the coupling of the graviton with the stress tensor. This is like the first leading cubic interaction between some minimally coupled scalar. Of course, remember that because we're looking at observables in field theory, H mu nu has gauge degrees of freedom that need to be fixed. So in this case, one fixes it with a covariant gauge. And then we focus on the regime where S, the Mandelstam variable S, is very large compared to the momentum transfer effects T. And we look at leading diagrams that are leading in very large energy. So these are trans-Planckian energies, as I said. And the dominant diagrams turn out to be what are called the ladder diagrams, which are drawn at the bottom. The first one is the tree diagram. The second one is one loop. The second and third are one loop diagrams. Remember that I'm just looking at a cubic interaction where there's one graviton and two scalar fields arising from the stress tensor. So there are no graviton self interactions in this diagram, but they can be added. And then there are 6 two-loop diagrams and so on. It turns out that all of these diagrams can be very remarkably resummed, and you can compute the amplitude exactly to all orders in perturbation theory. And that amplitude looks like so. The parameters that appear in this amplitude are things that I've already mentioned. So there's the square of the center of mass energy S. G Newton is the coupling constant. T is the other Mandelstam variable. And this amplitude can actually be written as an integral over some unique function, which I write to the bottom, called chi. It's called the iconal function. Notice that there's a new parameter mu. This is an infrared regulator. And this is necessary in flat space because in particular, as you run in the loops, this graviton can go on shell and you get a pole. So you have an infrared divergence that you need to cure with some regulator. This has very interesting relations to symmetries near infinity, BMS symmetries and so on. Maybe we'll come back to that at the end. But in flat space, the amplitude needs a regulator that needs to be put in to make sense of it. So it looks like one can compute gravitational or quantum gravitational amplitudes. To some extent, you could also argue that this is a classical amplitude because I've represented this also as a shock wave, which is a nonlinear solution to classical Einstein's equations. So of course, this is not a general feature of gravity that you cannot compute everything in effective field theory. So the natural question is, where are the black holes? And as I said earlier, black holes are intermediate states that we think appear when impact parameters when you start reducing impact parameters, when it starts competing with the length scale associated to the scattering. So in particular, you can start to reduce this impact parameter, repeat iconal amplitude calculations, and one observes that these amplitudes diverge if you pretend that this is just flat space. So this suggests that there's an intermediate state that is produced. And this is again a statement that gravity is special, that there are quantum effects that arise not only due to momentum transfer, but also because there are intermediate emergent scales that appear. So in this case, you want to think of the Schwarzschild radius that appears because G Newton is dimension full. So now we want to understand how you can bring black holes into the picture. But let's go sort of chronologically in how we progressed from this stage in the past. Before understanding black holes, what were better understood are actually stringy corrections. So how do these go? As I said, there's a Schwarzschild radius, which is given by G Newton times square root of S. And we take this to be much larger than Planck scale, because we want to avoid any ambiguities with Planckian physics. There's also the string length, square root of alpha prime, which we also take to be much larger than Planck scale. So we're looking at perturbative strings, where the string coupling constant is very small. So in total, we have 3 length scales in the game. There's the impact parameter, there's the Schwarzschild radius, and the string length. The flat space iconal that we just looked at is in this regime, where the impact parameter is much bigger than all the other scales in the game. And you can start correcting this flat space iconal by perturbative parameters, which is Schwarzschild radius over the impact parameter, which is very small, and then string length over the impact parameter, which is again very small. More pictorially, what do these look like? The green pictures, I've color-coded them appropriately. So this, what's called the H diagram, is a classical correction because it comes from Schwarzschild radius over impact parameter corrections, but there are vertex corrections which arise from more ultraviolet scale. So that's more like a quantum correction. And you can start looking at subleading corrections to the entire iconal resummation. And this is very well studied and by a lot of the authors that I wrote at the top of the slide. There are many more that I haven't written here. There's actually also several nice papers by Steve Giddings on this. Another regime that you can look at with the same 3 scales that we have is the exact diametrically opposite regime, where the string length is much bigger than the impact parameter, and it's also bigger than the Schwarzschild radius. What does that mean? Imagine that you're colliding particles. The impact parameter is so small that you first hit the string length. So that means that before you produce any classical black holes, you start exciting strings. So stringy effects first appear in this regime before any classical black hole formation effects appear. And it was observed that as you take the string length to approach the Schwarzschild radius, starting from this stringy dominant regime, there is expected black hole-like behavior, namely that final momenta or external momenta appear to go as 1 over the size of the black hole. And this is an interesting regime for various reasons, because you could study different aspects of it. So look at the formula at the bottom left. You can tune the quantity on the left-hand side, the Schwarzschild radius over the string length, to be much smaller or much bigger than 1 just by tuning G string. And this goes under the name of black hole string transition, where you can start looking at black hole-like behavior or stringy behavior. The third regime that's interesting is the one that we'll focus on today, which is that you have impact parameters that are roughly of the order of the Schwarzschild radius or smaller, but we still take the impact parameters to be much bigger than the Planck length. And again, by tuning G string, you can try to probe the black hole string transition, but now in the case where the classical black hole production is available. So these are all the corrections that people have studied over a long period of time in the last 2 or 3 decades. And what we want to do now is to understand this regime where impact parameters are smaller, where black holes do come in the picture. And that's what I want to move on next. But let me pause to see if there are any questions.
Actually, I have a question now.
Yes.
Yes, please.
Yes.
Please,
Aisha.
go ahead.
Good afternoon. Thanks. I do not see clearly what do you mean by Schwarzschild radius bigger than impact parameter. Of course, I understand a small impact parameter, but if you have impact parameter smaller than Schwarzschild radius, you are in, you are in the interior of the black hole. I mean, I assume this is just the last sentence in the previous slide, the regime you highlight. Yes, the last is some said to illustrate, but it's not rigorously correct. You cannot write, the impact parameter will be smaller than RS. This is what could be written after. Do you confirm or you interpret that what you have is a production or a black hole formation afterwards, after after you interpret that as a black hole formation. But from the beginning, there is, this sentence just at first degree is that you are in the interior of the black hole, and so, well, you need to treat the problem perhaps differently.
Excellent question. I agree with the sentiment. And if I was all powerful, I would not raise, for example, the notion of which regime of impact parameter space I am in. I would just compute amplitudes in general for all impact parameters. And one would hope that when I take impact parameter to be very large, I recover the flat space iconal amplitudes. Whereas as I tune impact parameters to be smaller, at some point, I would learn something about exactly what you're saying, the collapsing problem. And strictly speaking, the way I write it, it's not entirely well defined. So what I'm going to do as we go on, perhaps this will become more clear in a few slides, is I'm going to think of this scattering process as two particles scattering in the presence of an already existing black hole. So I'm not imagining these particles to actually collide into collapse to form a black hole, because I don't have the power to treat this completely dynamically collapsing problem. But I'm going to approximate, or I'm hoping that one would understand the scattering processes with particles that are interacting at short distances near the horizon in the presence of an already existing black hole. And secretly at the back of my mind, what I'm thinking is that in some regime, this is going to teach me something about black hole formation or some aspects of dynamical aspects of black holes. But your criticism is completely valid that I'm not treating the completely dynamical picture where this notion of a Schwarzschild radius is not exactly well defined because the horizon is building up in a collapsing problem. But I hope that in a few slides, what I'm trying to do becomes a little more clear.
I also have a quick question. Three questions.
Yes, please.
So first, regarding the first point, is flat space iconal. So maybe I missed the point, but so by doing this flat space iconal computation, you can reproduce this classical shockwave metric. Exactly.
Correct.
Right.
Correct. So what you can think of is take flat space, consider a test particle that's moving on flat space, and you ask, in the presence of another particle that I drew, for example, if you think of the red particle that I drew earlier, right, this back reacts on the geometry, and you can ask, what is the change in the geodesics of another test particle in the presence of this back reaction?
Okay.
And you can interpret this change in geodesics as an amplitude from before the shock wave to after the shock wave. And this gives you an amplitude, the change in the wave function. And this change in the wave function exactly coincides with the Feynman diagrams that we do.
Okay. You get really this correction to the metric that goes like a logarithm.
Yes, exactly. In fact, you can even look at, there's a lot of interesting work since a very interesting paper by Thibaut Damour in 2016, where people are trying to understand how scattering amplitudes or classical scattering amplitudes teach us something about classical gravity.
Sure, sure.
So the relation between amplitudes and solutions to equations of motion. And there's a nice paper by Andrea Cristofoli in 2020, I think, where they show that from the scattering amplitude from the three vertex, you can exactly derive that the metric correction coincides with the Eichelberg sexual shock wave.
Okay.
And there's a more general proposal by the same author, Tim Adamo and Piotr Turkin, more recently, a few months ago, where they also argue that something similar holds in curved space, which to some extent, it's also what I'm going to say in the next slides, where in this case so far, it's all about classical back reaction. And I want to argue that there are certain things that classical gravity does not capture. And you will start seeing this in Feynman diagrams that I'm going to draw in the upcoming slides.
Okay, thank you.
Thanks for the questions. Any other questions before I move on to smaller impact parameters? Okay, if not, let me move on. So I'm looking at the same picture again, where I have two infalling particles. The impact parameter, there's no Schwarzschild radius here in what I'm writing, as you see. The impact parameter I'm taking to be much bigger than Planck length, but I'd like the impact parameter to be somewhat smaller than g Newton times square root of s. And I want to take the energies of collisions to be not trans-Planckian, but we have an emergent scale, the mass of the black hole, or this g Newton, inverse of g Newton times square root of s. So this scattering picture that I'm going to draw is going to be valid even when energies of collisions are very small, because the mass of the black hole is going to come to the rescue, such that the equality that we need to satisfy, for instance, to compute something like the Eikonal diagrams, is much weaker. It's applicable for a much wider range of energy scales. The flat space Eikonal was only valid when energies of collisions were trans-Planckian. Whereas here, as you see, it's very difficult to violate this condition, the second condition that I write here. So in contrast to the flat space Eikonal, we had impact parameters that were much bigger than all other scales. And the center of mass energies of the collisions were much bigger than the Planck mass. So let me return to this question again of what happens in a collapsing problem. So if you have some infalling matter that's radially falling in, here I just took it to be null matter. So an apparent horizon forms well before, even before the matter has actually crossed what you would later interpret to be the Schwarzschild radius. And that apparent horizon in a collapsing problem grows as infalling matter accumulates. And then at some point, at late times, long after collapse, this apparent horizon would essentially look like what we would call the Schwarzschild horizon or the event horizon. And the time it takes for this black hole to collapse and form is much smaller than the entire lifetime of the black hole, because the black hole evaporates very slowly, especially if it's large. So for most of the lifetime of the black hole, essentially what we would think of as the apparent horizon coincides with what we would call the event horizon. And this is exactly what Hawking was also using, that for most of the lifetime of the black hole, except in the very initial stages and the final stages of the black hole evolution, that the apparent horizon is essentially the same thing as the event horizon. And that's why we look at infalling matter in the presence of an already existing black hole. And the statement I want to make is that if you're thinking of a green particle that was forming the black hole, it experiences essentially the same metric as the red particle. So infalling matter that is towards the end of the collapse, once the black hole is almost settled, it experiences an already formed black hole metric. And that's why I'm just going to forget the dynamical process, because I don't know how to describe this entire process as a classical solution even in higher dimensions. I'm just going to think of matter that is falling in to an already existing black hole. The ambitious logic I'm trying to propose here is just that I'm hoping that thinking of these red particles scattering in the presence of an already existing black hole is going to teach me at least something about the last parts of the collapse, where the black hole itself is not very dynamically changing, and most of it is sort of formed. So now what I mean by small impact parameters is I'm going to think of two particles whose transverse distance, which are interacting near the horizon of an already existing black hole. And that means that their transverse distance is bound by the size of the sphere, which is the size of the radius, of the size of the horizon. So they can be much smaller than the radius of the horizon if I just take them to be close enough on the horizon, or they can be at the opposite ends of the great circle, and then they would be roughly of the order of the Schwarzschild radius. So I'm going to just focus on a Schwarzschild background. I'm thinking of particles that are propagating in the presence of a Schwarzschild background, but I'm going to allow for metric fluctuations. I want to improve upon Hawking's calculation by not assuming that the metric is fixed, but I look at metric perturbations that contribute to these interactions. That's what I mean by small impact parameters, in the hope that it says something about evolution of a collapsing problem. But exactly what it says, I'm unable to define. I hope that answers the question that was raised earlier. So just like we did with the Feynman diagrams in flat space, I'm going to look at, again, perturbations away from this other vacuum solution, which is the Schwarzschild solution. And I'm going to look at scattering diagrams that are generated by the graviton coupled to the stress tensor, which now, again, I have a minimally coupled scalar field, just for simplicity. And I have to fix the gauge again to compute physical amplitudes. And as it turns out, because the metric is complicated, one would like to use as much symmetries as possible, because computing the propagator of even a scalar field, let alone the graviton, is not analytically possible in the presence of a black hole. So we'd like to exploit the symmetries that are available, for instance, spherical symmetry. And it's known that if you use the same covariant gauge, or the de Rondler gauge, it couples to different partial waves. So one would like to exploit the spherical symmetry of the background. And there's a very nice paper by Regge and Wheeler in 1957, where they propose that you can decompose the graviton into partial waves, where all the different partial waves decouple. And that parametrization is what you see on the equation on the right-hand side of your screen, where the metric is split into what are called even and odd modes. The even mode is the block diagonal one, and the odd mode is the other one with X. Of course, this is the symmetric matrix. So HAB is now the longitudinal direction. So it's a 2 by 2 matrix. And then K is a transverse scalar on the 2 sphere. So the even mode has 4 degrees of freedom. HAB is a 2 by 2 symmetric matrix. So it has 3 degrees of freedom. K is 1 transverse scalar. And then there are 2 degrees of freedom that sit inside X in the odd parity mode. So in total, these are 6 different degrees of freedom inside the metric, inside the graviton. And the Regge-Wheeler gauge essentially has gauge fixed the other 4. So that we have all the available physical off-shell degrees of freedom. And notice that expanding a scalar field in spherical harmonics is easy, but the moment you have spin, there are what are called tensorial harmonics to make sure that all the independent degrees of freedom are not 10 independent scalars or 6 independent scalars, but they form a spin 2 field. And that means that there are tensorial harmonics, which in this gauge reduce to simple spherical harmonics. And all the different spherical harmonics decouple, as I said. What we also noted was that if you take the momenta of these particles that we are scattering, if you take the transverse momenta of these particles to be small, that the odd parity graviton does not contribute to leading order. It's just a technical simplification, but these are all things that one can add to compute subleading contributions to what I'm going to say. So in particular, I'm choosing the background to be the Schwarzschild background, and I'm going to expand the graviton perturbation in this Regge-Wheeler gauge. So in general, you have an action that looks like the following, where you have a quadratic term that comes from the longitudinal modes small h, little ab, and you have a coupling term that takes HAB to K and vice versa. And then you have a quadratic term that is just for K. Because we split the graviton into this weird, quote unquote, weird gauge, you don't have diagonal degrees of freedom. And that's why you see that HAB couples to K. But this is just a gauge artifact. And then there's, of course, the interaction term. So what I wrote down explicitly is the quadratic graviton part. And then you have the interaction term and the free scalar part. Now, the propagators of the graviton are defined by this complex matrix equation because all the quadratic operators are now coupled. So we're looking for these curly p's, which are the propagators. It's useful to just look for a moment at how these graviton perturbations look explicitly. So H mu nu we split into H plus and H minus, so the even and odd parity modes, as I said. The even mode was block diagonal, and this is how it explicitly looks. And now it's apparent that when you have a scalar field that you expand in plane spherical harmonics, all the angular dependence sits in the spherical harmonics, and what multiplies it is angle independent. Whereas here you see that because it's a spin 2 field, that there is some remaining angular dependence that sits inside in the tensorial mode itself. What's important to note is that I also wrote down gauge transformations or diffeomorphisms that we use to fix the degrees of freedom that I said we fix, all to get rid of the 4 redundant gauge degrees of freedom. And those can also be expanded in partial waves, as I wrote at the bottom right top corner. So psi small a and psi capital A. And you see that the angular part of the diffeomorphisms come with derivatives on the spherical harmonics. So in particular, there are no angular diffeomorphisms for the 0 mode because YLM is constant. And you see that the odd parity mode comes only with derivatives with respect to the angles on the spherical harmonics. So for the S wave, if you wish, there is just no odd mode. There's no H minus. And there are still 2 gauge degrees of freedom that we need to fix in H plus. So depending on which partial wave one is looking at, there are certain simplifications, redundant gauge degrees of freedom that one has to be careful about. But for all the details, you can look at our papers. But I wanted to point out that this is something slightly non-trivial that one has to be careful about. That in certain modes, even though you think that you fixed the gauge, there are still some redundant gauge degrees of freedom that one has to be careful about, in particular for the L equals 0 and L equals 1 mode. So now what we do is in this partial wave basis, we go near the horizon. In general, I haven't done anything so far except write everything in a complicated looking basis. So I'm still unable to invert for the quadratic operators to find the propagators. However, now we take a near horizon limit where we are approximately near the horizon, and there we are able to invert the quadratic operators to find the propagators. The reason why we're able to do this is because near the horizon, essentially, the metric is a product space, which you can see here from the metric. If I set small r equals capital R, the Schwarzschild radius, it becomes a product space. And the longitudinal part of the metric is essentially conformally flat. So you can while rescale all your fields, and essentially you get some effects coming from the while rescaling without any loss of generality, but you can use flat space Mandelstam variables to define all your kinematic variables near the horizon. So it's sort of a reason why you were able to do this near the horizon. And you end up with Feynman rules that look like the following. The scalar field, which is in the left top, has a familiar propagator where you see that there is a mass term. So I took a massless scalar field, but there's a emergent mass term that's essentially an artifact of the curvature of the spacetime. It goes it's inversely proportional to the Schwarzschild radius squared. And lambda is the partial wave in question. It's L squared plus L plus 1. So for a large black hole, it's essentially a very small mass. For the graviton, however, you have a propagator that looks like the right top corner. And you see that there's a part of it that looks like flat space, as I said, which is just a bunch of etas with a factor that sits in front, which tells you that there's some infrared soft piece. So if you set the momentum dependent part to be 0, for example, you do not get a pole, which is very different to what happens in flat space. And then there is this momentum dependent piece, as I said. Now, we haven't gotten rid of any UV divergences because if you sum over all L's, which is like resumming the Kaluza-Klein tower, we have a quadratic action at every partial wave. But then if you resum everything to all else, then you will recover your UV divergences that you expect. But it looks like in this basis near the horizon, there's a natural infrared regulator that's given by this FL, or the size of the horizon. So in particular, there's no soft pole inside the propagator. And the coupling constant is now a dimensionless coupling constant, which is what I call gamma, which mediates the interaction, and it's M Planck over M black hole. So this theory is legitimate or reasonable whenever gamma is small. So whenever we have a large black hole. And if you look at the propagator again at the right top corner, you see that when I set L equals 0, lambda equals 1, and the momentum dependent part of the propagator flips sign because of the lambda minus 3 in the denominator. And similarly, if I set L equals 1, lambda becomes 3, and the propagator has a pole. This is not a pole in momentum space, so it's not a physical pole, but this is again reflective of the fact that there is some redundant gauge degrees of freedom in these monopole and dipole modes that we need to additionally fix. These are some of the details that I'm working out to present a comprehensive picture of the graviton propagator with Nico, and that should appear in a week or so. But these are things that were also pointed out by Renata Kalos and Adel Rehman last year in a couple of nice papers. So putting things together, let's zoom out a little bit and look at the scales in the problem again. We have 3 mass scales. There's a Planck scale.
I have a question in the
yes, please.
I'm a bit confused. So there is gauge redundancy for both L equal to 0 and L equal to 1,
Correct.
right? But for L equal to 0, there is no pole here for the propagator, but L equal to 1, there is a pole. So
correct.
What is the difference between these 7?
This is just a gauge artifact. Once I write down, once we fix all the degrees of freedom in the metric perturbations, once we fix all the gauges, then there is no pole for the L equals 0 and L equals 1 mode. You should just interpret this propagator as only valid for L greater than 1. And for L equals 0 and L equals 1, there's just a slightly different formula.
Okay, but when you do this different formula, so you should do separately for L equal to 0 and L equal to 1.
Correct.
This should be separate, totally separate.
Correct.
For L equal to 0. Okay.
Correct. They should be treated separately. They will end up giving you formulas that look somewhat similar.
Okay.
But they should be treated separately.
Okay. Thanks.
Perhaps one thing that will make it clear is let's focus on the L equals 0 mode. You see, I just told you that.
I'm sorry. Can I ask a question?
Yes, please.
So your action is quadratic in gravitons, quadratic in scalar field, and cubic in interaction. Is it true?
Correct.
Why there is no quadratic interaction?
Excellent question. I could include quadratic, cubic, quintic interactions all the way up to infinity. I just took the leading interaction.
Okay, thank you.
Okay, please continue if there is no more questions.
Okay. Yeah. So there are 3 scales in the problem, as I said. There is a Planck scale, there's a black hole mass, and the energy associated to the scattering. What we're going to do is to compute quantities perturbative in E times m black hole, such that over m Planck squared. This is analogous to taking Transplanckian scattering in flat space. And we're going to resum infinitely many diagrams, like in the flat space iconal, where the vertex coupling constant is now m Planck over m black hole. So you could call it perturbatively exact or non-perturbative. And the consequence of the left-hand side is that there will be only soft diagrams that contribute, meaning that the gravitons that are exchanged turn out to be 0 momentum, only in the 2 to 2 amplitude. But there will be infinitely many Feynman diagrams that contribute because of the ladder expansion. So physically speaking, what I've said is that because the background is spherically symmetric, essentially we separate longitudinal and transverse effects. We take transverse momenta to be small. And I said that we want the impact parameter to be small. By that, and we achieve that by scattering particles near the presence of an already existing black hole, such that the transverse distance is bound by something like the order of the Schwarzschild radius. And then there's an emergent scale that allows for very low energy collisions, which is the black hole mass, such that our expansion is valid for all energies that satisfy this limit. So what I'm going to do now is to look at scattering amplitudes that arise from these, from all the Feynman rules that I just derived for you. The first one is just the tree diagram. In principle, the cubic diagram has a vertex, which has, if you expand it in partial waves, it in principle splits the angular momentum arising from, say, P1 to the graviton and P3. At every vertex, you have a sum over Clebsch-Gordon coefficients. depending on the partial waves that you're in. To leading order, you can assume that one of the legs is fixed at every vertex to be, say, at the S wave, such that the equations become simpler, so that we ignore the Klebsch-Gordon coefficients, just to make formulas that I will present easier. But in principle, this is something that one can compute. You can just leave your Klebsch-Gordon coefficients in the interaction term in the vertex and carry out everything that I'm saying. Perhaps some integrals will be harder to compute, but in principle, everything that I'm saying follows regardless of making this assumption. But this is just to simplify some things. So this is a tree diagram. You have 2 one-loop diagrams, 6 two-loop diagrams, and so on. So a general n-1 loop amplitude, or an amplitude with n exchanged gravitons, can explicitly be computed. And it's again determined in terms of one iconal function. And you see that things are very simple here, because we are now writing everything for each partial wave in 2 dimensions. And we have infinitely many partial waves, of course. And as I said, the soft limit is enforced upon us. And this can be seen as a consequence of the fact that we're looking at amplitudes that are perturbative in energy times m black hole are much greater than m Planck squared. You will have subleading corrections, which are heavily suppressed by 1/e times m black hole. What's also an interesting thing to notice is that if you compare this iconal function in the partial wave basis to the flat space iconal, in the flat space iconal, you have the amplitudes are dominated by highly rotating modes, where the L squared times the plus L appears in the numerator of the amplitude. Whereas for the black hole, the amplitude is dominated by the low L modes. So there's a physical difference between the two of them. And there are probably many consequences of this that need to be explored. It's an observation that's good to know. You can resum each of these loop amplitudes, and they neatly resum into an exponential again. And that exponential can be written down. And we also showed that this 2-to-2 amplitude has a classical counterpart, which is now a shock wave in the presence of a black hole. In flat space, the 2-to-2 iconal was a shock wave in the presence of flat space, whereas now we have a shock wave in the presence of a black hole. However, notice in the bottom right corner, in the exponential, you have an 8 pi g Newton over L squared plus L plus 2. The shock wave amplitude turns out to only give us L squared plus L plus 1. Whereas the Feynman diagram approach gives us a discrepancy of this additional factor of plus 2. And it's in the beginning, it's a little puzzling until you realize that the shock wave is essentially an on-shell solution to nonlinear Einstein's equations. Whereas here we have amplitudes that are mediated by virtual gravitons, where each of these internal gravitons need not be on shell. They are allowed to be virtual because they're not external legs. So it's actually remarkable that in the flat space case, all the virtual gravitons are also on shell, because they give you a perturbation that gives you a nonlinear solution. Even in the black hole case, perhaps because things are so simple in the 2-to-2 amplitudes, that all the extra off-shell configurations in these amplitudes, all the off-shell gravitons do is to just renormalize this constant. In principle, they could have changed the amplitude dramatically, but there's a physical origin for this additional factor. But this is the story of the 2-to-2 amplitudes. One thing you should have probably thought to yourself or complained about is that why are we looking at 2-to-2 amplitudes? In principle, if I throw something into a black hole, I expected the black hole to spit out many different particles, for example, Hawking radiation, and not just an out state which has only 2 particles. So in principle, we'd actually be interested in 2 to n amplitudes or m to n amplitudes, but for simplicity, I'm looking at 2 to n. So we're still in the same regime of phase space, but we're now interested in what happens when you have n particles coming out for arbitrary n. And you actually expect that this n has some physical significance for it to be related to the black hole size, for instance. That the dominant n should be somehow related to the number operator or the number associated to the black hole degrees of freedom. So the Feynman diagrams look like this, where you have 2 particles where they exchange gravitons, and you have all, in this case, I only included 3 vertices that come from the graviton coupled to the stress tensor, but you could correct this diagram by including all kinds of other interactions. And this tree level diagram is sharply peaked about a certain specific value of n, which is given by E squared times G Newton. And if you put E equals M black hole, and it's an interesting question as to why I should choose E equals M black hole, it turns out that this is sharply peaked around an N, which gives me the entropy of the black hole. It's an observation. In principle, this is sharply peaked about some N that is correlated with some fixed energy E. And you suspect that this energy may have something to do with the mass of the black hole. And of course, just like we did by computing subleading corrections to the 2 to 2 iconal, you could in principle ask what are the general corrections that are allowed in my theory, where I have 2 to n amplitudes. And this is what I like to call a cobweb amplitude, where you can have arbitrarily many virtual graviton exchanges between any two external legs. And this might be interesting for endpoint iconalization. So far, we only understand 2 to 2 iconalization. We understand something called the chaos bound for 4-point functions, for 4-point OTOCs, out of time order correlation functions. There's a nice set of literature on this, why that's important. But in principle, it looks like maybe there is an endpoint chaos bound, or at least some new exponents that appear from higher moments and not just 4-point functions. But unfortunately, these turn out to be very difficult to compute. However, there's a subclass of diagrams that one could compute, which I call the ladder of ladders, because this is or maybe I should have called it a chain of ladders. So far, there's nothing special about these diagrams. It's just something that we realized that we could explicitly compute to all orders. So you could resum all of these and you get an amplitude that can be explicitly written out. It's not clear what is special about these. And perturbatively, one could correct this to include general cobweb diagrams, but we were unable to resum all of them for endpoint functions. So what's the physics behind these 2 to n amplitudes? There's actually, it turns out that there are very interesting physical scales that emerge from these amplitudes. One of them should have already been obvious from the sharply peaked tree level amplitude. Let's look at a quantity that's defined in terms of the scattering matrix called the time delay. It was introduced by Wigner and then slightly corrected or improved upon by Eisenberg in a PhD thesis that's very nice. So consider a resonance E0 and look at the scattering matrix near any resonance with some positive energy width. By definition, the scattering matrix has a pole because of the resonance. So the scattering matrix looks like what I wrote here in the first equation. There's some slowly varying function or some constant function of E in the numerator. And there's a pole when E equals E0. And you have an analytic continuation that defines for you the width. The time delay is defined by the imaginary part of the derivative of the log of the scattering matrix. Seems like an arbitrary definition, but if you think of your scattering matrix as a pure phase, for example, e to the I delta, you see that this time delay is essentially trying to capture the derivative of the delta of the exponent of the phase. And if you evaluate this for a scattering matrix above, you get a formula that has that goes as 1 over E at near the resonance. So this tells you that every time you have a resonance, this formula for the time delay gives you the lifetime of this resonance, because this the resonance has energy E or E0. So this is a time delay that tells you that if you have scattering processes, some dynamics happens and then you have out states, and you ask, how long do my scattering particles spend in the scattering region? How long do I have to wait before I receive information from the scattering problem? And that depends on the lifetime of the intermediate resonance that's formed. It's sort of physically intuitive. Now you can ask, we've computed 2 to 2 scattering amplitudes and 2 to n scattering amplitudes. You can ask, what are the time delays associated to these? And here's what you get when you apply this formula.
Can I ask a question?
Yes, please.
So, I mean, that relationship between the time delay and the energy, isn't it something that would follow from the time energy uncertainty relationship also?
Yes, I think the derivation, let me try and recollect. Yeah, I think you're right.
Okay. I mean, is it something different that is going on here? That is not.
Well, you see that depending on how complicated the potential is, even though your uncertainty relationship is the same, the more complicated the potential, the longer that your scattering particles will spend in the scattering region. Right. So this is really a property of the dynamics.
Okay, thanks.
Right. So for the 2 to 2 amplitude, we find a time delay that looks like Gm or m black hole times the log of G times E, where again, if you set E equals m black hole, you get m log m. And for whenever there's particle production where you have 2 to n amplitudes, this looks like G squared times m times E. And this gives you, again, when you set E equals m, G squared times m cubed. For those of you that are familiar with these quantities, you see that the first quantity is what is called the scrambling time, m log m, and the second one is what's called the page time or the half-life time of a black hole. So it's very interesting that if you have elastic scattering, that this does not probe the long scale of the gross properties of the state itself, but it probes for you the dynamics of the near horizon region. However, if you have particle production in the game, then it seems to probe the macroscopic properties of the black hole itself, because it tells you that if you throw 2 particles in, you have to wait for half the lifetime of the black hole before you receive this information again. In particular, what this means is that if you wait half the lifetime of the black hole, you start receiving information. And therefore, if you assume that the theory is free and you ignore these interactions, you would miss information. So this is a statement that Hawking's free field theory breaks down after page time, because information starts to come out. The particles that you threw in start to emerge. And this is, we are still in local effective field theory. It's just something that piles up over time, an effect that you otherwise miss.
Again, just want to ask, how do you get these expressions from what you showed previously?
I take the scattering matrix and I apply this time delay formula. So I explicitly computed the scattering matrix from the Feynman diagrams, and then I just plug this formula in.
Okay, so this energy E is what you get from that computation.
Correct, because there's the scattering matrix has a Mandelstam variable S, which is E squared.
Okay, thanks.
Any other questions before I move on to the last few minutes of my talk?
Yes. Is it true that you mentioned that entropy appears in your computations?
Sorry, can you repeat that, please?
Is it true that you said that the entropy occurred in your computations?
What about the entropy in your calculation?
Yes. Yeah. So it's a good question. I don't know a sharp answer to this, because you see that I'm computing this scattering matrix and I'm computing these time delays in terms of the energy E, and I'm manually putting this energy to be m black hole. And then I get the entropy out kind of trivially, meaning that you can think of the entropy as the multiplicity of the out states. And I told you that the amplitudes are, this n, the number of particles that are coming out, is sharply peaked around some energy. If I fix that energy to be the mass of the black hole, then I get the entropy out. But I don't have a first principles derivation of why that should be the case. So I see that the energy appears from these things, but I cannot derive it from first principles.
So you expect that the entropy is related with multiplicity?
Yes, I think the entropy is related to the multiplicity of the dominant n number of particles that are emitted.
Okay.
Can I ask
Let me move on. Yes, please.
So in this expression, you put E equal to MBH, right? What if you take E much greater than MBH? Do you get scattering amplitude similar to Minkowski one? Because when you put much larger than the black hole mass, it's basically scattering Minkowski space-time. Black hole is particles do not see the black hole. So
yeah, I'm not sure. It's a good question. I'm not sure if the calculation that I'm doing remains valid if I bombard the black hole with energies that are much greater than the size of the black hole.
Okay.
Presumably, I will form a much bigger black hole. Yeah, I'm not sure how to think about it.
Yeah. I mean, in that sense, it's possible to check the cross-check the calculation, right? I mean, like if you recover the Minkowski limit, then I mean, intuitively, I would expect you should recover the Minkowski amplitude if you take E much greater than.
Presumably, yeah. I'm not sure. I haven't thought about it carefully. It's a good question.
Yeah. And another question, can I ask another question? So
Yeah,
before
sure.
you mentioned that in the Minkowski eikonal phase, your scattering amplitude grows with L.
Yes.
Okay. And so here in this case, in the black hole case, the low L are dominant ones. How to understand this physically? So I mean, why
Yeah,
this
physically, what I don't know if I have a very sharp answer, but one way you can think about it is that if you throw two particles into a very large black hole, it's very unlikely that you destroy the spherical symmetry of the solution. So the thing that dominates are S-wave perturbations of the large solution. That's one way to think about it.
Okay. Well, here in this case, even you're considering, you said in the beginning, if you take impact parameter large, you again reach Minkowski limit, that is asymptotically Minkowski limit, right? So again, does this happen in your calculation that you reach your amplitude with high L dominance will happen in your amplitude if you increase the impact parameter much greater than the radius?
If I was powerful enough to write an analytic expression for the scattering matrix as a function of the impact parameter, then I would be able to do this. But as you see in my amplitudes, the impact parameter does not appear in explicitly. I'm assuming that the impact parameter is small, and therefore I end up with scattering near the horizon, but I don't have an analytic interpolating function that maps from small impact parameters to large impact parameters. If I had such a thing, then I could vary it and then check. But what you should think of what I'm doing is that it's giving you the other end of flat space. And so if you were to produce an analytic expression that gives you that captures both the physics, then in one limit you should expect the flat space, and the other limit you should expect what I'm computing here.
Okay. Thanks.
Okay, in the last 2 or 3 minutes, let me quickly go through the emergent soft limit that I spoke about all the way at the start. So Weinberg showed that there are these nice soft theorems that appear in flat space, where consider some n ingoing particles that interact and produce some m outgoing particles. And now let's consider an extra graviton that comes out. So let's consider the amplitude corrected by an extra graviton. He showed that the dominant diagrams are where one of the outgoing legs produces this graviton, or one of the ingoing legs produces this graviton. And looking at the small q limit, where you take the graviton momentum to be small, so it's soft, he showed that there's a nice factorization where you get this factorized quantity that shows a pole when q goes to 0 in the square brackets, where the amplitude with the graviton, which is on the left-hand side of the equation, is given in terms of this factorized soft product, this soft factor times the amplitude without the graviton at all. That's why the m on the right-hand side has no indices. So he showed that amplitudes with an extra graviton are related to amplitudes without the gravitons, where there's a soft factor that appears in front. And this appears in the soft limit where q goes to 0. But q is, of course, a dimension full quantity. So what we want to say when you take this, if you don't exactly take the q equals 0 limit, but you're taking a near 0 expansion. So what we actually mean by this is that q over m Planck goes to 0, because that's the natural dimensionless quantity. Another way of saying is that we take m Planck to be very large, or g Newton to be very large, and therefore, g Newton to be very small, and therefore that's where your perturbation theory in flat space is valid. And that's why in the soft factor, you see g Newton appearing as a prefactor, the coupling constant. Now, when you have a black hole, you cannot naively take the q over m Planck to 0 limit, because we're working in the presence of a large black hole, where gamma m Planck over m black hole must be small. So you have to be careful with when you take m Planck to be large, because as you take m Planck to be large, you also have to say what happens to m black hole such that gamma is somehow small. And you have to say also what happens with q over m black hole. And it turns out that there is a new emergent soft limit that appears when both these conditions are satisfied, where Q over M Planck goes to 0, but M Planck over M black hole goes to 0 much faster. If both these limits are satisfied, you can show, I haven't written down the soft theorem on the slides, but you can trust me, and it's going to be in an upcoming paper with Ankit Agarwal, that there are emergent soft theorems that appear using the Feynman rules that we derived when you take this emergent soft limit, where because you have an extra scale, you have to define what you mean by softness carefully. And if you do this properly, there appear to be new soft theorems. And we're deriving this in an angular momentum basis because all the Feynman rules that I wrote down were in a partial wave basis. So it's very interesting to understand what these emergent soft theorems are. And for those of you that followed the literature relating to soft theorems that have a new avatar in the last decade or so, where soft theorems have been shown to be Ward identities, especially in flat space. There's a very nice paper by Strominger and collaborators, a series of them actually, where they show that Weinberg's soft theorems can exactly be shown to be Ward identities associated to BMS symmetries that appear at null infinity. And we also know from some work by Laura Donnet and collaborators and several others that there also exist BMS-like symmetries near the horizon. So you can ask whether the soft theorems that emerge from the soft limit that I just told you about, whether they correspond to Ward identities of these BMS-like symmetries near the horizon. If they fill up somehow whether there's any relation and if they're identical even. For this, one needs to understand soft theorems both in flat space and in the black hole case in an angular momentum basis. That's something that I'm working on together with Ankit, and hopefully that should be some work that appears soon. Let me conclude with that. What should you take away from what I've presented in this talk? There's a remarkable new phase in quantum gravity which seems to capture some properties of black hole evolution. And the information paradox seems to be addressed in this phase with no UV completion necessary. There seem to be emergent soft theorems which are different but analogous to Weinberg's flat space soft theorems. And you can extend everything that I've said to include stringy corrections and treat the black hole string transition. There are several aspects that are analogous to flat space iconal, which is very well studied, that are waiting to be discovered in this phase. There's also a very natural order G Newton expansion away from the leading iconal in the 2 to 2 amplitudes. And that's in flat space that goes under the name of the post-Minkowskian expansion. And one can ask what physics is captured in what seems to be a natural post-black hole approximation. There's also some interesting features of gravitational echoes that I didn't have the chance to mention in this talk, but we've written a paper about it with Panos Betsios and Olga Papadoulaki. There's some further ideas that I've listed explicitly that might intrigue some of you. But with that, let me thank you for your attention and take more questions.
Okay, thank you very much for your very interesting talk.
Thank you.
Questions, please. Norma, please, the first question is from Professor Norma Sanchez. Norma, please ask your question.
Thanks, Irina. Thanks for this talk. I still have some points on your conclusion and coming back to the small impact parameter regimes or results. First, in your previous slide, please, if you can come back to just to the conclusion, but the first, yes, what should we take away? I must agree, I mean, with all the sentences or conclusions you list there, but the first one, I do not see too much. I mean, in your presentation, of course, in the aim and in the framework, I see, but remarkable new phase of quantum gravity capturing black hole evolution. I don't see here too much quantum gravity in the description. Of course, at the beginning you present, but it's perturbatively what you treat. And then when you, and this came to the black hole formation for small impact parameters. And then came to the question for the black hole you form. I mean, are these black holes, which are big black holes, the same of the black hole, or they have different properties of the black holes that we know? I mean, and this is the first question.
So one way I could answer this is to say that if I look at Hawking's computation, would you call that quantum?
No, this Hawking computation is very well known, that is semi-classical gravity, and that is semi-classical, it's very clear. And then you cannot call quantum gravity, you can call quantum matter, and that is semi-classical gravity.
Excellent.
And,
so
and then you add set corrections, but in the way I have seen in your presentation, is perturbatively.
So so if you look at, if you call Hawking's calculation semi-classical, I'm including perturbations of the metric. So I guess this you would call as perturbative quantum gravity.
Yes, I mean gravitons.
Okay.
You are considering gravitons, and this is perturbative quantum gravity.
Correct. So that's what I wanted to. That's strictly speaking, that's what I'm doing. However, notice that there are infinitely many such corrections. If you take the 2 to 2 amplitude, for example, there are infinitely many corrections that one is able to compute. So this is, at least for certain observables, this is perturbatively exact.
Yes, but I mean,
so
I
think particular, sorry, just to finish my thought, what I want to say is that there are certain observables for which one is able to compute things perturbatively exactly. In particular, that means that you're able to extract exponentially suppressed effects.
Exponentially
suppressed effects.
Yes.
Because one is calculating things perturbatively exactly to all orders, to all loops. So now that's what I'm trying to do. Some people, depending on literature, depending on choice, some people might call it quantum, some people might call it perturbatively exact, but that's the physics of what I'm doing.
Yes, perfect. I mean, it's clear. Okay. So excuse me, I take the time, but I think it's important to clarify, I mean, to clarify the point. And so, this, I mean, all this program, the question came, what is, if I take this point, I mean, your point of view. So I can compute exactly perturbatively with perturbatively quantum gravity. I mean, summing up all corrections, all graviton corrections, I can construct a Schwarzschild or black hole metric.
This I don't know. What I'm trying to say is that if I sum up all the perturbative corrections that exist, I get strong corrections to Hawking's computation after page time. That's my conclusion. That after page time,
you have as a zero order the set Schwarzschild or the classical black holes, and then you have corrections.
Correct.
And so you have corrections to the known black hole.
I have corrections to Hawking's computation.
this is the point. Is your black hole, your zero order you find, and then you find the corrections. Of course, you have here different couplings, and I mean, it's clear. But this zero order is the known black hole, or is changed?
The zeroth order, I'm working in the background field method. So the zeroth order is the background that is there. That's the known black hole.
And you don't
I'm
change.
looking at corrections away from
Yes.
that.
Yes, and so you are adding corrections to the known corrections. I mean, we know stringy corrections or quantum corrections. These are small corrections.
I'm adding corrections that are not stringy, and these are not from the ultraviolet.
Yes, but there are small corrections. And what do we know we want now? I mean, I think we share our program, I mean, and others, including myself. What we know is to have a picture in which the black hole or what replace the notion of black holes in true quantum gravity, non-perturbatively, is some object which replace black hole, or which is a black hole differently, and in true quantum gravity, and it is what, in some sense, you have corrections, but this is not enough to perhaps could answer, or to begin to answer some problems, of course, because the semi-classical gravity or semi-classical quantum gravity is incomplete.
Professor Sanchez, may I just try to elucidate the point that you're trying to make? I think is that what Nava is doing is not non-perturbative, right? Am I correct in saying that?
I find these terms sort of difficult, because if I take gauge theory, one would call an instanton non-perturbative, and is in particular, if I'm computing one loop determinants like the BPST instanton, one would call that non-perturbative corrections to QCD or Yang-Mills theory, right? Whereas now, in principle, what I'm doing is something analogous, where instead of working in the true vacuum of the theory, which is flat space, I'm working at some non-perturbative solution, and I'm computing one loop effects and subleading corrections to an excited state. Using analogy with gauge theory, one might be tempted to call this non-perturbative. So it's a bit confusing. I would call this perturbatively exact corrections to Hawking's computations. And I'm saying that if you compute sufficient number of these corrections, they give you a sufficiently large contribution away from deviations away from Hawking. However, I think what Norma's point is that this is not an ultraviolet description. And that is absolutely true. That I'm working with effective field theory, and one can compute subleading corrections that deviate further from what I'm doing. And in principle, if you have an ultraviolet description, that would completely overhaul what I'm doing. So this is not a complete theory in any sense.
Right, you're taking the limits, right, where the much less M-Planck.
Yes,
Okay.
Or M-Planck over.
I could also include transverse momentum effects.
So
for example.
Okay.
Norma, at sufficiently high.
Yes.
Are you finished your discussions with?
No, thank you, Irina. And what Nava said in the last statement, I agree. I mean, this is not ultraviolet complete.
Complete.
And
okay.
What you have is some complete or exact perturbative corrections. But my point, and that is good. But my point is that is not enough to go to to complete semi-classical or Hawking description of the black hole. And the more complete, I don't know if we could speak about complete. I mean, what it could be everything, the theory of everything. But the more complete is going to more ultraviolet complete and saying that this parameter you have, or this complex, M Planck, Planck mass over black hole mass, you should not keep small, because with that you are very limited. You are very limited. I mean, you are very limited in gravity to go through. I think the issue is to go to Planckian physics, or to try to go to Planckian physics. I mean, and Gerard go in this direction too. But now, I mean, you are considering perturbative.
I think we would all love to have a...
Yes, I finish now. You try to complete the perturbative description in some way, if we can state in this way. You have to have a complete perturbative, a more complete perturbative description. But that,
I think,
yes,
I agree with what you're saying. The only takeaway that I would probably suggest is that one might have thought that you needed ultraviolet physics to find large deviations from Hawking. What I'm saying is that even before you go there, there are large deviations already in a perturbatively exact calculation. But as you say, it's completely legitimate that there's no Planckian effects that are visible here, and this theory does not capture any Planckian effects. It's an important question.
And precisely when you go near the horizon, and you need Planckian physics, and this is one of the first Gerard points. I mean, in the because of these descriptions of the ingoing and outgoing scattering through the horizon. I mean, this is and this you need Planckian physics, and the more easy way to take this is precisely not working in perturbative gravity, not working with graviton, but with the equivalent effective metrics, which are these gravitational shock waves, because are entirely non-perturbative. And that was the idea of Gerard I mean, in the 80s to use the scattering, gravitational scattering, using the Penrose, I mean, or Axel Sechs gravitational waves, even shock, or I mean, whatever you can.
Can I ask my question? If that's okay.
Yes.
Yeah, indeed. Maybe we should move to other questions, because people are.
Okay, maybe
okay.
we do. Thank you very much, Norma, for your questions. And the next question is from Deepak White. Please.
Yeah. Thank you, Irina. I'm sorry to cut you off, Professor Sen. Nava, I guess my question is that you are dealing with scattering of massless particles, right?
Right.
So there exists a very nice formalism, right, called the spinor helicity formalism, which allows you to calculate.
Excuse me. What is the name of formalism? Spinor
helicity.
Ah, spinor helicity. Okay, thank you.
Spinor helicity, right? So which allows you to calculate amplitudes to all loop orders, right? So that you wouldn't have this issue that you're having with like not being able to sum these cobweb diagrams and so on, right? So now I'm not sure how that formalism works in curved space-time, or whether it works, but perhaps that is something that could be useful for you.
Perhaps I don't know much about the formalism, but I also don't know if one can calculate off-shell amplitudes.
Right. No, that is a on-shell formalism.
Yes. So,
but I mean, ultimately, we want on all our answers. We want to ask about on-shell quantities only, right?
Yeah, that's right. So I don't. Can one include off-shell contributions in the loops, for instance?
Yeah. No. So the great thing about that formalism is that everything is on-shell. always.
But there are contributions to loop diagrams which are not
Absolutely. No. So that's the thing. Now it avoids that issue completely.
Okay.
It gives you the same answers, but it avoids the need to go to
I see.
off-shell terms.
Okay, I don't know anything about, I don't know much about the formalism, especially in curved space, so I'm not sure.
Right.
Perhaps there is some use to it. I don't know.
Okay, let's go to the next questions. The next question from Hilbert Batista Chivata. Please ask your question.
Hi, thank you. So thank you for this very nice talk. It's very, very interesting indeed. So I do work a bit on, this post-Minkowskian computation, covering of classical observables from scattering amplitudes, and it's actually very interesting what you're doing. So I have first a comment about the UV completion and how we understand this when you do this post-Minkowskian computation is that, even though you are doing, scattering amplitude, you may think this is quantum, but, the reason why this is classical or not UV complete is in the sense that, for instance, in your 2-to-2 scattering amplitude, you do not allow for closed, say closed graviton bubbles, for instance. So yes. in your diagram, you cut out all of these contributions. So those are the UV.
Correct.
Like, the quantum contributions that you will need to take into account for doing.
Right. For the moment I include
theory of gravity.
Cubic graviton interactions, then I'm forced to include bubbles, for example. Exactly.
So that's a point. So I have a question regarding, at the very beginning, you mentioned something that, this mass regulator that you need to introduce for the iconal phase is somehow related to BMS and perhaps the soft theorems. Can you comment a little bit about
so that? The statement is that if you choose your vacuum to not respect all the symmetries of your theory, then you end up with infrared divergences. So the claim of Strominger and co. is that infrared divergences are a consequence of not choosing the right vacuum. In particular, the vacuum that we choose at spatial infinity for asymptotically free states, this is degenerate because of all the BMS symmetries that act on it. And the claim is that if you choose a vacuum that respects all the symmetries, then you do not end up with infrared divergences. There's a nice paper by, this is also discussed in the lecture notes by Strominger on infrared structure of gravity. So there's a discussion on it that you can look at.
Okay, great, thank you.
In some sense, this is a generalization of quantum electrodynamics, which was discussed by Polish and Faddeev many years ago. Yes.
Right.
Okay.
I have a final comment, just because.
The next question is from Chris Ripkin. Please, Chris, ask your question.
I think Hilbert had a last comment, or.
I thought Hilbert has another question.
Very short comment, but regarding the spinor helicity that was mentioned, it's just like another way of doing computation, but in the spinor helicity you compute on-shell amplitudes and then you can glue them through cuts, for instance. And then in that way, you compute the loop amplitudes and everything. But,
Okay, good.
Okay. Thanks.
Thank you. Okay, Chris, please ask your question.
Yes, I hope the question is rather short. There was something that I noticed, I think, on page 30 when you showed the graviton propagator. And that was that the, yes, this one. So the term proportional to the etas, which is the identity term, does not contain a 1/k² mode. Does this mean that the graviton doesn't propagate here? Is that to be expected, or what is the physical intuition behind this?
The physical intuition is that, in particular, when you have L equals 0 or L equals 1, all the degrees of freedom are gauge. And so there are no degrees of freedom left that are propagating. And that's why you have a momentum independent propagator for the low-lying modes. In particular, the 2-to-2 amplitude is dominated by the k equals 0 sector of this. And therefore, the contribution that is important, the dominant contribution to 2 to 2 iconal amplitudes, is the k equals 0 regime, where the graviton is actually not propagating. It doesn't carry any momentum. And the way to think about it is just that we have particles that are not exchanging momentum, but they're exchanging a soft virtual graviton.
Yes, that I see, but this propagator is valid for any L, right? Not only for, actually it was valid only for large L, because
this
engagement
expression that you see is valid for every L greater than 1. And for L equals 0 and L equals 1, you will find a propagator that is completely momentum independent.
Yeah, okay. But
so it's even worse than what you see here. That's what I want to say.
Yeah, but don't you expect then that for L larger than 1, there should be a kinetic term for the identity part? Because now there seems to be absolutely no degree of spin 2 degree of freedom that propagates.
Well, no, this thing propagates because you say when k equals 0, there's no pole.
Well, I mean, if I compute the propagator in flat spacetime, then the identity tensor structure has a 1 over k squared. So
that's
the
right.
flat limit seems to be a bit weird
here. So here you cannot take the flat limit precisely because I'm working, this propagator is only valid near the horizon to linear order. So you cannot go far away. If I were to produce an analytic expression that is valid globally on the space-time, then you can take the flat limit and then you will recover your 1 over k squared. But this is only valid near the horizon. So you should think of this as ripples on the horizon that are not valid far away.
Okay.
Okay.
Yeah, thanks.
I saw questions from Luca Benafante. Luca, do you want to still ask a question?
Maybe, if there is time, I can ask. Actually, maybe I already asked you once. Is about this page time that you get. And of course, you get exactly the page time if you assume that center of mass energy is of the order of the black hole mass, which in principle is not the case if you just scatter some initial states that you prepare.
Correct.
And again, so which is nice, I mean, that you get anyway a formula. But if I take energy which are smaller than the black hole mass, still within the regime of validity of your analysis, basically that square root of S times m black hole is larger than m Planck square. Okay. You can still, given this inequality, you can have energies which are smaller than black hole mass and still satisfy your regime of validity.
Correct.
And if you scatter this particle, you can indeed have like 2n time scale, which are can be a lot shorter than page time.
Correct.
So you can start having like information retrieval even faster than page time. How would you see that? Like,
correct. So one way to think about it is that there's something special about E equals m black hole, because when I throw these particles with the center of mass energy E, essentially the energy that is now in the black hole region is 2 times m. Instead of, because it was originally m plus E, there was a black hole mass m, and I add some energy E to it, and that is m plus E, which is now 2m.
Okay.
Right? And then if I consider processes that conserve momentum, then I'm reducing this 2m size black hole into half. Right? Because I get out all the energy that I threw in.
Okay.
The fact that this reduces into half is a property only visible if you choose E equals m black hole. And if you have m plus E where E is not m, and then you choose momentum conservation, you wait for all these particles to come out, the black hole hasn't come out yet. So essentially from all the thermal correlations that you receive, it's not clear that you will be able to actually say that you receive information because the black hole hasn't reduced into half its size.
I
see. You believe that the black hole scrambles all the information?
I understand. In that case, will not be anyway half mass of the black hole.
Exactly.
But anyway, what is interesting that even if you have small energies, you have anyway a logarithm, a neb cube, e square times m black hole time scale, okay, which
correct.
is
So it's linear in M. However, the important thing is, okay, there's one thing that I haven't included in my construction at all, which is that I treat the ingoing modes, scalar modes, and outgoing scalar modes. It looks like I expand them in the same modes, right? I don't take into account the fact that there's a difference in the vacuum of ingoing modes compared to the outgoing modes. That is why if I put my interaction terms to 0, I don't get Hawking's answer, right? I get some trivial non-interacting answer, which is just the identity. So there's a difference in vacuum. So there's a thermal prefactor, if you like, that comes from Hawking, which is exponentially suppressing my amplitudes. And only if I take E equals M black hole do I counter that thermal prefactor. If I take something smaller, the thermal prefactor of Hawking still dominates whatever I think I'm getting out from my calculation.
Okay, I see.
So what I'm trying to do now with one of my students is to write sort of a all-encompassing formula where you also take into account the discrepancy in the vacuum, such that you can compare which amplitude is in dominant, which contributions do you have to sum up, such that you counter the tree level result.
Okay, thank you. I understand.
Okay, more questions? I see one more question from Norma. Norma, please ask. I'm sorry, a short question. Okay.
Yes, I'm sorry. I don't know if I am allowed to ask one more. Question.
Okay,
but,
ask, please.
Thank you.
I'm very happy that I've captured your interest.
Thank you. Yes, the exponential suppression factor you have, in fact, appears too in other, in other previous computation, even with the stringy calculations or graviton. In several computation appear this factor. The previous one. Ciafaloni, Amati, Veneziano, etc. And they interpreted that as the presence of Hawking or black hole. And what you have is the same, or this prefactor, you have something, of course you have more corrections, but for the prefactor, you don't have any changement of that.
What I actually have is that, so I don't have the exponential suppression because I haven't incorporated Hawking's tree level effect into my calculation. However, I have an exponential growth, which comes from this large amplitude.
Yes.
If I resum all n here and use Stirling's approximation, I get an exponential. So what I have is that these amplitudes are exponentially growing with a real factor, which is exponentially growing. And this is the one that cancels the exponential suppression. So what I have is an exponentially large contribution, if you will, not suppressed one. I have to combine it with the exponential suppression that one expects from Hawking. And then I want to say that you get an order one, you get something that is unitary.
I see.
Okay. More questions, please? I don't see any. Okay, let's thank the speaker once again. Thank you very much. You've presented a lot of very interesting material. Very interesting material.